Hello everyone. My name is Jay Vadaria. I am a student of Department of Architecture Regional Planning, Indian Institute of Technology, Kudgapur. Today, I'm excited to talk about support vector machines, which is one of the most popular algorithms used in machine learning. What is a support vector machine? It is a supervised machine learning problem where we try to find a hyperplane that best separates the two classes. Don't get confused between SVM and logistic regression. Both the algorithms try to find the best hyperplane, but the main difference is logistic regression is a probabilistic approach whereas support vector machine is based on statistical approaches. There are two types of support vector machine, linear SVM, nonlinear SVM. When the data is perfectly linearly separable only then we can use linear SVM. Perfectly linearly separable means that the data points can be classified into two classes by using a single straight line, if 2D. When the data is not linearly separable then we can use nonlinear SVM, which means when the data points cannot be separated into two classes by using a straight line, if 2D, then we use some advanced techniques like kernel tricks to classify them. In most real-world applications we do not find linearly separable data points, hence we use kernel trick to solve them. Support vectors, these are the points that are closest to the hyperplane. A separating line will be defined with the help of these data points. Margin, it is the distance between the hyperplane and the observations closest to the hyperplane, support vectors. In SVM, large margin is considered a good margin. There are two types of margins, hard margin and soft margin. I will talk more about these two in the later section. Let's understand the working of SVM using an example. Suppose we have a dataset that has two classes, green and blue. We want to classify that the new data point as either blue or green. To classify these points, we can have many decision boundaries, but the question is which is the best and how do we find it? Here, since we are plotting the data points in a two-dimensional graph, we call this decision boundary a straight line, but if we have more dimensions, we call this decision boundary a hyperplane. The best hyperplane is that plane that has the maximum distance from both the classes, and this is the main aim of SVM. This is done by finding different hyperplanes which classify the labels in the best way, then it will choose the one which is farthest from the data points or the one which has a maximum margin. Now let's see what is dot product. The dot product can be defined as the projection of one vector along with another, multiplied by the product of another vector. Here A and B are two vectors. To find the dot product between these two vectors we first find the magnitude of both the vectors, and to find magnitude we use the Pythagorean theorem or the distance formula. After finding the magnitude we simply multiply it with the cosine angle between both the vectors. Mathematically it can be written as A. B equals A cos B, where A cos is the projection of A on B and B is the magnitude of vector B. Now in SVM we just need the projection of A, not the magnitude of B. I'll tell you why later. To just get the projection we can simply take the unit vector of B because it will be in the direction of B but its magnitude will be 1. Hence now the equation becomes A dot B equals A cos unit vector of B. Now coming to use of dot product in SVM, consider a random point x and we want to know whether it lies on the right side of the plane or the left side of the plane, positive or negative. To find this first we assume this point is a vector, x, and then we make a vector, w, which is perpendicular to the hyperplane. Let's say the distance of vector w from origin to decision boundary is c. Now we take the projection of x vector on w. We already know that projection of any vector or another vector is called dot product. Hence, we take the dot product of x and w vectors. If the dot product is greater than c, then we can say that the point lies on the right side. If the dot product is less than c, then the point is on the left side, and if the dot product is equal to c, then the point lies on the decision boundary. You must be having this doubt that why did we take this perpendicular vector w to the hyperplane? So what we want is the distance of vector x from the decision boundary, and there can be infinite points on the boundary to measure the distance from. So that's why we come to standard. we simply take perpendicular and use it as a reference and then take projections of all the other data points on this perpendicular vector and then compare the distance. Margin in support vector machine. We all know the equation of a hyperplane is w.x plus b equals 0, where w is a vector normal to hyperplane and b is an offset. To classify a point as negative or positive, we need to define a decision rule. We can define decision rule as, if the value of w.x plus b greater than 0, then we can say it is a positive point, otherwise it is a negative point. Now we need w(b) such that the margin has a maximum distance. Let's say this distance is d. To calculate d, we need the equation of L1 and L2. For this, we will take few assumptions that the equation of L1 is w.x plus b equals 1 and for L2 it is w.x plus b equals -1. Now the question comes, 1. Why the magnitude is equal? Why didn't we take 1 and -2, 2? Why did we only take 1 and -1? Why not any other value like 24 and -100, 3? Why did we assume this line? Let's try to answer these questions. 1. We want our plane to have equal distance from both the classes, that means L should pass through the center of L1 and L2, that's why we take magnitude equal 0.2. Let's say the equation of our hyperplane is 2x plus y equals 2, we observe that even if we multiply the whole equation with some other number, the line doesn't change. Hence, for mathematical convenience, we take it as 1. Now the main question is exactly why there's a need to assume only this line. To answer this, I'll try to take the help of graphs. Suppose the equation of our hyperplane is 2x plus y equals 2, let's create margin for this hyperplane. If you multiply these equations by 10, we will see that the parallel line, red and green, gets closer to our hyperplane. We also observe that if we divide this equation by 10, then these parallel lines get bigger. We can now say that these lines will move as we do changes in w(b), and this is how this gets optimized. Coming to kernels in support vector machine, the most interesting feature of SVM is that it can even work with a nonlinear dataset, and for this, we use kernel trick, which makes it easier to classify the points. Suppose we have a dataset like this. Here we see we cannot draw a single line or say hyperplane which can classify the points correctly. So what we do is try converting this lower dimension space to a higher dimension space using some quadratic functions, which will allow us to find a decision boundary that clearly divides the data points. These functions which help us do this are called kernels, and which kernel to use is purely determined by hyperparameter tuning. Now, what is advantages of SVM? SVM works better when the data is linear. It is more effective in high dimensions. With the help of the kernel trick, we can solve any complex problem. SVM is not sensitive to outliers, can help us with image classification. SVMs are effective in high-dimensional spaces and with a small number of samples. SVMs are robust to outliers and can handle non-linearly separable data by using kernel functions. Now, disadvantages. Choosing a good kernel is not easy. It doesn't show good results on a big dataset. The SVM hyperparameters are cost, c and gamma. It is not that easy to fine-tune these hyperparameters. It is hard to visualize their impact. SVMs can be computationally expensive, especially when using nonlinear kernels and large datasets. SVMs require careful selection of hyperparameters such as the kernel function and regularization parameter. So thank you for watching my video, and don't forget to enjoy your day.